Okay, so welcome to lecture 30. This is going to be on the multi-transistor circuit. So we're going to analyze that circuit using our inspection analysis formulas. Just a couple of announcements. First, your lab 5 you know is due next Tuesday. Probably be a good idea, well, you have to be done by next Tuesday, so to have your design done, etc., because that will help you on your exam. You saw me just erase the homework 10 thing. There is no homework 10 due next Friday because there's no homework during an exam week. And so your exam is going to be next Friday at 7 p.m. in 160 Krober Hall. Review session is going to be next Tuesday, 6 to 8 p.m. in 400 Corey. That's where your TAs will run that review session. Similar to the last one, I suppose. The midterm info sheet will be online today, and we're going to discuss that in class today. And I will hand out some sample midterms today as well. I might do that halfway in the class to make sure everyone is here. So I guess those are my announcements. Any questions about anything? How's that lab going?
Is there going to be a lab next week?
On Monday?
Or no, Wednesday, Tuesday?
No, there's no lab for Wednesday.
Starting lab 6 next week is what I'm...
Yeah, we're not going to start lab 6 next week, I suppose. I mean, I may pass out lab 6 on Wednesday. Lab 6 is going to be one of these things where it doesn't matter which session you go to for the lab. It's just, you know, it's open season. You go to the lab when you can, any of the sections in that sort as you're doing it. And lab 6 in the beginning is going to be mainly design and that sort. But I'll probably get you lab 6 by Wednesday next week. There's no lecture 2 on Monday next week, right? Everyone knows that. So I guess the question is, will the lab be open on Monday? I guess the answer is going to be no, but you can get in anytime you want, but I'm not sure that you can get to the cabinet, you know, during that period, unless you contact one of the GSIs who may or may not be around to show up. So, okay, how's everyone doing on that lab? Everyone finished? I know there's a lot of people that are done with the lab and that are writing right now. So I think that's a good sign. Any other questions about anything? Logistics? Okay. So last time we went through that inspection analysis sheet, and I think I'm going to bring that up again just to jog your memory of what that was. So that's this, which had all these formulas that you ought to have memorized, and I sort of went through them all and said, you don't really need to memorize all of these even. There's really only 4 or 5 that you need to memorize, maybe 6, depending on how you want to do your problems. If you want to do Miller transformation, if you understand how to do that, then it becomes 5. You know, if you neglect things like common collector frequency response, the time constant due to the C pi capacitance across the base to the emitter for common collector, which we discussed why you could do that last time. We'll even discuss that again this time because that will show up in the example that we do. And there's only 4 so far equations that you need to memorize. Okay, so there's not a lot of equations you need to memorize that will allow you to actually go in and do inspection analysis. And so hopefully you've been memorizing these equations so that you can keep up with me as I do this problem in lecture today. And so let's go ahead and attack that problem that I'm talking about. And so that is right here, this one here. Okay, so as an example, I'm going to analyze this multi-transistor amplifier. It's only got 2 transistors. Your lab 6 is going to have 4 probably, or as many as you want to use, but you probably will need to use 4. And lab 6 will be 4 maximum that you can use. But this is a 2 transistor example here. And so we want to do this inspection analysis, and I want to do the usual thing that we're looking for in any amplifier. So I want to find input resistance, output resistance. So let's say find input resistance, output resistance, gain, which I'll call A sub V. That'll in this case be V0 over Vs. And let's get the high frequency response. So I assume you can get the low frequency response too. It'll be the same fashion as we've done it in the past using the large capacitors, but I won't do that in this example here. And so first we can look at this topology here. So I've got one transistor, two transistors. If I look at this first transistor, I can look at it and sort of immediately tell that I'm biasing this up the same way that we've always been biasing these things. So that stable bias circuit that we came up with that uses this voltage divider of R1 and R2 to set the base voltage of Q1, which then sets the emitter voltage, which then sets the collector voltage. So in that order is the way that we're sort of setting these voltages for the DC biasing of this thing. And then we've got a second transistor Q2 that's following this here. And one thing you want to do when you're doing inspection analysis is sort of recognize what kind of amplifier we have here, what kind of stages we have here. So if I were to look at this first stage here, what kind of stage is that? If I ask that question. I'm looking for something like common emitter, common base, common collector, common emitter with degeneration. Recognize this? Yeah, it's common emitter with degeneration. And the way you do that, and we'll do this in detail in a bit, but you recognize this is a large capacitor that shorts out this RE, but this RE stays. And so this is just like, I'm taking the gain from the base to the collector. And so that kind of gain is either going to be common emitter or common emitter with degeneration. So I have this resistor, it's common emitter with degeneration. Okay, then the next stage that I have right here, what's this? Again, common base, common emitter, common collector, common emitter with degeneration. What's happening here? There's my input, there's my output. What you're really looking for is what's common, so what's grounded. And you're looking for the AC ground. Yeah, common collector, because that's ground right there. Right? In the AC circuit, this goes to ground. So this then becomes common collector. And for me, as soon as I hear common collector, the gain is 1. Right, so immediately that's what I'm going to be thinking. But I won't analyze it that way. We'll take a little bit of time to do that. But so we've recognized what kind of amplifier this is. And you can do this even without that recognition. You don't have to recognize that to go places with a problem like this. But you can't get anywhere with this unless you can actually get the small signal circuit for Q1 and Q2. Okay, and they're each going to have different small signal circuits because they're each going to have different bias points. So in this problem with two transistors, you have to determine the small signal elements for two transistors. So you have to do it twice. And before you can get any of these small signal elements, you have to get the DC operating point. So in this thing, what I have to say here is that first, find the DC operating point. That means you have to find all the currents going through all the devices. So at the very least, you want the collector current through Q1 and Q2. Right? That's what you need to get the small signal elements, R pi, R naught, GM. But when I ask for DC operating point, I'm asking for the voltages at all the nodes and the currents through all the branches. And so that's what we're going to go ahead and do. And so let's first identify some of the things we already know. So this R1 and R2, remember that's generating a current going through that we used to call I bias. So I'm going to call that I bias as well. But since this is for the first stage, I'm going to call that I bias 1. Okay? And this voltage then right there is going to be the voltage at the base of Q1, so I'll call that VB1. And of course the current going into the base of Q1, the DC current, is IB1. And so if I have a good design here, and so if you're doing design right now for Lab 5 and for Lab 6, you'll do similar, quote, good design. What do you want to happen here for you to have a good bias design, which means you want a stable bias point? Okay, well the rule that we came up with for this is you want this current I bias 1 that's going through those bias resistors R1 and R2 to be greater than 10 times IB1. It's another way to say that I bias 1 you want much greater than IB1. So if you can achieve that, then you're going to have a fairly stable bias point. Okay? And so hopefully this has been designed that way, because I'm not designing this, I'm analyzing this right now. And so the first thing I want to do is get this VB1. What's the voltage at the base of Q1? Well, that's just going to be the voltage divider R1 and R2. Assuming that I've designed this so that I bias 1 is greater than 10 times IB1. If that's the case, then I could ignore the base current going into IB1. Okay, and I can treat this just like a voltage divider, so that I could say that VB1 is just the voltage division between R1 and R2 times the voltage that's the input, which is VCC here. Okay, so that now becomes VB1. That equation there. Okay, as soon as I get the voltage at the base of 1, what do I know about the voltage drop across the base to emitter of Q1? I know that that's equal to a VBE on, what we called VBE on before, which is pretty much 0.7 volts. Okay, we're just going to assume that. It's not actually 0.7 volts, 0.68945, whatever you want, but we're going to approximate it by 0.7 volts because it doesn't deviate much from that no matter how much current you have through Q1. Okay, for reasonable types of circuits that we work with. So in this case, with that, knowing that voltage drop, I can then immediately pick out what the voltage is VE1 at the emitter of Q1 there. So that VE1 then just becomes whatever VB1 was, which is given by this equation, minus the VB on voltage, which for all intents and purposes is 0.7 volts. Okay? And so now I can keep marching on with this. If I have this VE1 here, that means I can get the current through the emitter, which is essentially the same as the current through the collector. And I'll make that look like a nice VE1 there. Maybe I'm incapable of doing that. But the current through the collector is going to tell me what the voltage at the collector is. So that's why I want the current through the collector there. I want this voltage right here, which is VC1. And so to get that voltage, I need IC1. So IC1 is going to be about equal to IE1. And I know that IE1 is just the voltage VE1 divided by both of these resistors added together. So it's going to be VE1 divided by RE1 plus RE1 prime. Okay, which if I plug in VE1 is just going to be VB1 minus VBE on divided by that sum of resistors. Okay? And so that gives me IC1, and if I know IC1, then I know VC1. Let me be consistent. Capital C's, I put a line through them. So then I know VC1, which is then going to be equal to this voltage VCC up top here, minus the voltage drop across RC1, which is just going to be IC1 times that RC1. Okay? And that then is also equal to the voltage at the base of 2. So this voltage here, which is VC1, that is equal to the voltage at the base of 2, which is at that same node, of course. So now I also know the voltage at the base of 2. And if I know the voltage at the base of 2, then I know the voltage at the emitter of 2, because there's just going to be a VBE on drop from base to the emitter there. And so VE2 is just going to be equal to VB2 minus a VBE on. Okay, so you see how I'm doing this? I'm basically starting at the left side of this whole circuit, and I'm getting this voltage here, which is what my bias string gives me, the bias string being R1 and R2. And then from there, I use the VBE ons of this transistor to get VE1. that gives me the current because I put a very definite voltage across these resistors, and that's how I create currents. Okay, that creates a current through RC1, which puts a drop here, and that allows me to get this voltage here at VC1. And then that also gives me the voltage at the base of 2, which then gives me the voltage right here, the VE2, which I just wrote the equation for. And if I go to the next page, I then can write that the collector current, which I need to get the bias, the small signal parameters for device Q2, IC2 then, is just going to be equal to IE2. Wow, how did that change? Okay, so I have, and so IE2 I know is just going to be whatever VE2 is divided by the resistor it's across, which is RE2. Okay, and so just some remarks in determining the DC bias point. So what I just did was determine the DC bias point of a multi-transistor circuit. You will always be doing this, doing it this way if it's a bipolar circuit. Okay, so the one thing you should do while you're trying to determine this bias point is look for the VBE ons. Okay, these things are a definite voltage that will set a definite voltage across a resistor somewhere. And anytime you have a definite voltage across a resistor, that is going to create a current. And that's how you find your currents. Okay, so VBE ons are a definite, or I'll call well-defined voltage. All of these are your well-defined voltages in this circuit. The other well-defined voltages are VCC and ground. Okay, all the other voltages you get by determining currents and determining the voltage drop across resistors. And so the second thing you find is that the current through the transistors, which is what you're mostly interested in, right? Because remember, GM is equal to IC over VT. You need IC. R pi, right, is beta over GM. Also depends on IC. R naught also depends on IC. That getting IC allows you to get that hybrid pi model element values. Get the hybrid pi model element values. So you want IC. And so you can get IC and other currents because they're usually determined by VE over REs. Okay? So you notice in the first stage, it was the voltage across these resistors that determined the current through Q1. In the second stage, it's the voltage across this resistor that determined the current through Q2. Okay? And so again, for bias stability, we already talked about the first stage, and I will mention it again. I want this current I bias 1 to be greater than 10 times IB1. That means I want that current to be a lot bigger than IB1. But at the same time, for bias stability, I have to worry about bias stability for the second stage. So I can write that also, if I'm looking at this right here, then this current going through Q1, which is IC1, I can also call that I bias 2. Right? So that current there is effectively my I bias 2. And so I can also say that IC1, which is effectively my I bias 2, that has to be greater than 10 times the current into the base of transistor 2 in order for me to have a nice stable bias point. Okay, so when you're designing your lab number 6, which will be a multi-transistor design, remember this. Okay, this is key to getting a nice design. You want to make sure that the current going to the next stage is a lot smaller then the current going to ground from the first stage. If that's not the case, you probably run into some issues after you hook this thing up, that your bias point is not what you think it should be. Okay? So try to remember this. If you don't remember this, I'm sure you'll run into it again, and we can help you in office hours or that sort. But that's a key thing for the bias. So now we've got the bias point for this. And the key thing that we got from the bias point are the collector currents, because the collector currents give us the hybrid pi model. I'm assuming now that you've got the hybrid pi model. And so now what you want to do is start getting these small signal parameters that we're searching for right here. Okay, and so the first thing we want to do is our midband analysis. So let's get our midband, let's do our midband small signal analysis. To get gain, input resistance, and output resistance. Okay, so now this small signal analysis goes the same way that you've done small signal analysis for the single transistor type amplifiers. What you need to do is take this large signal circuit that includes all the biasing here and create the small signal circuit out of that. So to do that, you know how to do that already. You're going to take this VCC and you're going to ground it. You're going to take this V capital S and you're going to ground it. All of these large capacitors, CB1, CE1, and CC2, which I've labeled large, you're going to short them. And what's left is going to be the circuit that you need to analyze. So here, let's start with Q1. And so Q1, I've got RC1 going into VCC, which now becomes ground for me. So there's my RC1. And then I have my transistor Q1 here. And CE1 gets shorted, so RE1 prime goes away, but I'm left with RE1 still. Okay, and that's my first transistor there. And this then is going to feed my next transistor, which is going to be Q2. Q2, there's no capacitor out here, so it's going to go straight into RE2. And C2 is going to be shorted, so this then is going to go to my output and straight to my load resistance, RL. Okay, and at the input I've got a couple things going on. I've got my source resistance, RS. I've got my source itself, V sub S, and then I've got the bias resistor, RBB, which I'm just substituting for R1, parallel with R2. Okay, so this is my small signal circuit. This is what I need to analyze to get my input resistance and my output resistance and my gain. And so the way I want to do that, and so you could do this by drawing in the hybrid pi model for Q1 and Q2. Okay, if you need to do that, do it. Okay, don't refrain from doing that just because I say it'd be nice if you can do inspection analysis, right? If you can't do inspection analysis, do this by plugging in your hybrid pi models. Do what's comfortable for you. I'm just hoping that by the end of the class you can be comfortable with what I'm about to do, which is inspection analysis on this. Okay, so if I want to inspect and analyze this, the first thing I want to do is get this resistor Rn. And Rn is usually going to be the resistor seen looking from Rs. Right? This is my source everywhere from here to the left. This is Rn from there going right. Okay, so the first thing I see with Rn, if I wanted to write its expression, is I see this RBB going to ground. So that's the first resistor I'm going to include in my Rn expression. So RBB going to ground there. But then I need to account for this resistor that I see looking that way. Okay, and that resistor is also going to ground, but it's in parallel with RBB. And so that resistor I'm going to put in parallel with RBB. But let's first get that resistor. So can anyone tell me what that resistor is going to be? I'm now looking into the base of Q1. Can anyone tell me now what that is? Okay, you have an R pi. I'll call that R pi 1 because I've now got different transistors. So R pi 1 plus times the RE1. Right, exactly. That's what it is. And so to write out this input resistance equation, I'm just going to put that right here. If I wanted to, I can call it beta 1 plus 1. Let me do that just so you can see how specific I'm being to the different transistors here. Okay, and so right away we have our input resistance. Just by inspection, we've done that. You can write out the hybrid pi model, you can solve the Kirchhoff's current law equations, you'll get exactly the same thing. Okay, so now let me go and get my output resistance. So usually my output resistance is going to be everything before the load resistance RL. Okay, but it depends, right? If I were to draw this arrow out here, then you would include that RL. Okay, and on an exam or anything, I will explicitly show in arrows like this, parenthetical arrows that tell you which resistance I'm looking for. Okay, so you don't need to worry about that. But now if I'm looking for that R0, what do I see? Well, the first thing I see is I've got some resistance here going to ground. And then I've got some resistance here. And you know, you don't think of that going to ground, but it is, right? There's ground there, there's ground there, there's ground everywhere. Right? So this is another resistor going to ground. And so those two resistors are going to be in parallel. And so I'm going to start writing this out. I know I have that RE2 there. And so that means my R0 is going to include that RE2. And that's going to be in parallel with some stuff that I see coming, looking up into the emitter of Q2. But now what do I see looking up into the emitter of Q2? Well, there's a couple things. So remember, I have Q2's R02 right here. Right? That thing is going straight to ground. And so that's one of those resistors that's also in parallel with RE2. Okay? So I can go up that RL2, but then I can go up the emitter this way. And so if I go up the emitter, there's where you have to remember that expression for what that resistance is going up into that emitter. And so what is that expression looking up into that emitter? You remember that? So remember, when you look into the base, you multiply this resistor by beta plus 1. When I look up into the emitter, I'm dividing by beta plus 1. Okay, so that's a good way to remember it, right? In one direction, you multiply by beta plus 1. The other direction, you divide by beta plus 1. But what do you divide by beta plus 1? Well, first I see an R pi looking up that way. That R pi is going to get divided by that beta plus 1. So that's R pi 2. I'm going to go ahead and write that R pi 2 there. And I know that everything that I write here, and I'm going to add more resistance from there, but everything there is going to be divided by beta plus 1, which I'll write in a little later on. But let me first add up all the resistance I see from here looking that way. So I see that resistance, R pi there, but now I got to worry about the resistance that I see looking this way. Okay, what do I see looking that way? I see a resistor up that way, and then I see a resistor looking down that way. Okay? And these are all resistors that are going to ground, as far as I'm concerned. So this resistor is going up into ground. So in this case, if I wanted to write that resistance, that would be RC1. Okay, and that would be in parallel with the resistance I see looking down into Q1. And so this is that R0 of Q1, but now multiplied by all the stuff that has to do with this emitter resistance and that base resistance. So remember, there's that big formula there, and that's the hardest formula to memorize. And so I'm going to go ahead and write what that formula says. That says 1 plus GM1 times RE1 divided by 1 plus whatever resistance I see looking out of the base of Q1. So I'm looking out of it. And so what I see there is RS in parallel with RBB. That's all that resistance looking out of the base of 1 down to ground. Right? Remember, this then gets divided by R pi 1 from that equation there. And so this becomes all that resistance that I see there looking in this direction. So I got to add that to R pi 2 here. So I'm going to add to R pi 2 RC1 in parallel with that R01 times 1 plus GM1 times RE1 divided by 1 plus RS parallel with RBB divided by r pi, that whole thing, and then this whole thing divided by beta plus 1, but specifically beta 2 plus 1, in case the second transistor has a different beta. Okay, so this now is one big resistance, and that now becomes my total R naught here. Okay, but you know, I have this equation in my mind. I've memorized that equation. But if you did not memorize this equation, you're in luck. Because if you think of this, this RE2 is usually not that big of a resistor, like from your lab using values like kilo ohms and that sort, right? This R naught 2 is big, right? This is a big resistor. Okay, this resistance right here is a big resistor right here. So I could sort of grab this, and I can say that that's big as well. Okay, so because, not the RC1, sorry, just the R naught 1 part of that. This part is big. Anytime I have big resistors in parallel with something else, I'm not going to worry about them. So this whole equation we wrote right here was not necessary at all. We do not have to write that equation, because what I'm going to do in the end to write out my R naught right here is that R naught is just going to be equal to, in this case, that RE2 parallel. I'm going to ignore that R naught 2 because it's big. I'm going to ignore this R naught 1 here, but I still have the rest of that. So it's a parallel with R pi 2 plus RC1, which is in parallel with that gigantic resistor, divided by beta 2 plus 1. And that now becomes my expression for R naught. Okay, so I went through a lot of work to do that, but I didn't really have to work that hard. Anytime I saw an R naught, I could have just ignored it throughout this whole thing and just written down the equation based on my inspection analysis formulas that I have memorized. And even if I didn't have the R naught one memorized, I was still fine. Okay? Any questions on what I just did to get those resistances? So hopefully you can see what I'm doing. I'm just looking in certain directions, and I have memorized the resistances looking into the different terminals of my transistors. I know what those equations are as a function of what's loading each of those terminals, and immediately I'm writing those expressions. Okay, so think of doing this by drawing out the hybrid pi model and solving a circuit that has two hybrid pi models in it, that has all that stuff. That would be not fun to do. I encourage you to do it so you can find out how not fun it is. So in a way, yeah, and so at some point you're going to ask me, and people have already asked me questions like this, what can I ignore and what can I not ignore? Okay, and so you may think that for me to be a good teacher, I should tell you what to ignore and what not to ignore. But actually that's the worst thing I can do for you. I'll tell you, but that probably is not good for you, because it's better for you to figure that out for yourself, because figuring it out is a lot of work. Figuring it out means you're going to draw a hybrid pi model or something, you're going to not ignore that thing, and you're going to get some huge equation. It's going to be horrendous. And then you're going to learn, okay, I could have ignored that. And then you're not going to forget that you could have ignored that. Right? You got to suffer a bit in order to learn what to ignore. Okay, that suffering is important. So if you ask me what to ignore, I'll probably tell you. But before I tell you, I'll tell you, I probably shouldn't tell you this. And then I'll say it. Right? But it's better for you to waste time in order to learn this thing, in order to better know what to ignore, what not to ignore. Okay, so at this point, so that I don't forget, let me go through some of the midterm stuff right now. So let me stop here and talk about the midterm stuff. Let me first pass out the sample exams. And if you have a friend who needs one as well, you can take a couple of them. Take as many as you need for your friends and stuff. But I'm also going to put these out in front of my office. I guess I should keep some for the TAs too here. Okay, give me the rest of them when you're done getting them there. But I'll put them out in the box outside my office as well. But this is the midterm exam that I gave last year. And so you can sort of look at it. You can see the types of problems that it has on it. I can almost promise you that the midterm exam that you're going to get includes some of this stuff, but will look different. Okay, because I never make it exactly the same. And so now let's talk about the midterm information sheet here. So here it is. And so we're going to do office hours like we did last time, like we tried to do last time. They kind of got canceled. Did they get canceled because of the PG&E thing? The Thursday office hours? They did, yeah, okay, yeah. Yeah, they got canceled because of the PG&E power outage. We're going to try to do that again. So Kieran's going to have, these are all extra beyond what we already hold. So our regular office hours we're going to still do, but these are extra on top of our regular office hours. These are the rooms that they'll be in, although you should check the website. I'm going to put this sheet on the website, but if there's updates to that, check this sheet. If you go to that room, you see someone else in there, or there's no one there, check this sheet on the website to find out where things may have moved. The review session is going to be Tuesday, November 12th, 6 to 8 p.m. in 400 Corey. I think I mentioned that before. The exam, you know when that is, next Friday, 7 to 9 p.m. That's in 160 Krober Hall. We looked for that last time. Okay, so someone's going to complain about this. So the exam is closed book, but you can have, I say, one here. I guess I acquiesced to some folks here, and I said 2. So I'm going to go ahead and change that to 2 right now. It doesn't matter. The exam, well, hopefully you won't have to use your cheat sheet that much, right? Because this is going to be an exam where time will be of the essence. Because you're going to have 2 hours, but remember, this is the type of stuff where recognition becomes important. So hopefully you're good enough to recognize that. And, you know, if you memorize the equation, be confident about it. Because what I see a lot of times, people keep checking their cheat sheets. If they keep checking their cheat sheets, that's time you're losing as you're doing this exam. You can write anything you want on this. On both sides of the paper, you can have a magnifying glass. I don't care. Whatever you want there. Bring a calculator to the exam. Exam should contain enough space to put all your work on its sheets. Show and include all your work on the exam sheets. That's the only way to get credits, to show the work. How did you get there? Good guesses are good, but they won't get credit. Okay, put your reasoning for things. Exam will consist of a few problems, each for the number of parts. Right, that's the most informative thing that you've probably ever read. So during the exam, make appropriate engineering decisions and approximations to simplify your analyses. I will ask you to calculate things. And I do that because I think it helps you to some extent. You can tell whether you're right or you're wrong, right, by just looking at the numbers. Material to be covered is reading in Sedgwick Smith, class lecture notes, handouts, labs, homeworks. The exam is meant to include all material covered so far in the class, but has a sharper focus on the more recent material. Okay, so guarantee you're going to see some transistor circuits on this. You will probably have some kind of thing that will test whether you really did your lab number 5. Do you know how to design things? Do you know, say something was designed not good enough and you need to change something to get it better, what would you change? The exam will probably test that. Okay, the exam will probably also test your ability to analyze a new circuit. So, right, you know the common emitter circuit inside out, but in some of your homeworks you've seen some different circuit configurations. And in the exam, I guarantee you'll see some different circuit configuration. Okay, and so you need to be able to solve that circuit configuration. So when you see something new, just stick to the rules. Okay, what are the rules? Big capacitors. Well, first you do the DC analysis. But then after the DC analysis, you want the small signal circuit. Big capacitors, they're shorted. Current sources are open circuited. Voltage sources are shorted. And you're left then with your small signal circuit. That's the part where people have the biggest trouble getting the right small signal circuit. And then the analysis after that, you know, varying degrees of trouble and no trouble there. But the first thing you've got to get right is the final circuit. Okay, so when you see the circuit, don't get scared. Just apply what you already know. And what you'll find is what you already know will simplify that circuit to something that probably is easier for you to analyze. It looks bad from the beginning, But after the small signal simplifications, it looks a lot better. Okay? So you need to understand concept of large and small signals and the need for small signal analysis. You need to know the large and small signal models for bipolar and MOS transistors and determination of small signal elements and parameters. The biasing of BJT and MOS amplifiers, so parameter independent biasing. So biasing for bias stability is what I mean by that. Frequency response calculations using open and short circuit time constants. Analysis of transistor amplifiers for such parameters as midband gain, midband small signal resistances, and frequency response characteristics. The design of common emitter or common source amplifiers, that's just like your Lab 5 design problem. You know, this entails choosing resistors and capacitors to satisfy a given specification. I might ask you to actually do a design right there. So what took you several weeks in your lab, I might ask you to do within the span of 2 hours. Okay, the operative word is might. I might do that, I might not. And so that's pretty much it, right? And so the coverage for the exam is to the end of this lecture. Okay, then everything after this lecture probably won't be on the exam, but that's an amoebic thing, right? Because what I do after this lecture is continuing to do things that we learned in previous lectures. Just, I'm going to continue this multi-transistor small signal analysis to get the high frequency response and the gain. Okay? Any questions about any of this?
Can we be given some draft papers in the exam?
Draft papers? Yeah. Well, what I'm saying is that the exam should have enough space for you to do everything, but did you find that not the case on the first exam? By draft paper, you mean just extra sheets of scratch paper?
Yeah.
I won't come with it, but if you want to have your own sheets of paper, you can, but I would rather you work on the exam itself, because if you work on your own paper and try to attach it, sometimes we miss the stuff when we're grading. So that's why I'd rather you put everything on the exam itself. Okay? But you're free to bring scratch paper. When you run out of stuff on your exam, you can use your scratch paper. Okay? And if you want to fake run out stuff by just drawing an X here and an X there, and then attaching your sheet, you can. But I wouldn't recommend that because it's easier for us to find things if it's on the exam sheets. Okay? Any other questions about the exam? Anything? Okay. Well, we have several more lectures. Well, actually 2 more lectures before the exam. I will lecture on the day of the exam. If no one shows up to that, that's fine. You don't need to be at that lecture. I mean, you're watching lectures on video here. And catch up with the lectures too if you're not caught up. I guess everyone here must be caught up, but people who are not here, that's a message for you. Try to catch up because what I'm seeing online is that everyone is caught up to like 2 lectures ago. I could see that by seeing how many downloads or how many views from my YouTube site. So I could see everyone is keeping up with the lectures, but there's like 2 lectures behind or so. And you want to catch up. Well, I guess you don't need to catch up because this exam is... 2 lectures behind will still be okay for this exam. But you should catch up, for your lab and everything else. Okay? All right, so let's keep moving on with the lecture. We still have some time left here. So let's now go ahead and get the gain of this thing. And we're going to do that using inspection analysis too. So let me switch to green here. Okay, and so let's get the gain. V0 over Vs. So how do we do that with a multi-transistor amplifier? So what I'm going to do is I'm going to label all the nodes in this thing here. Okay, like I did before. So let's label this node 1. I'll label that node 2. Node 3. And that'll be node 4. Okay, and so when I get the gain, I'm going to get the gain from node to node. Right, so when I say get the gain, what you should be thinking of is, okay, gain from node 1 all the way out to node 4. Okay, so to get this gain, what do? I first want to get gain stage by stage. So 1, of course, there's no gain. I have my Vs right there. So I need the gain from node 1 to node 2 first. And I guess I can write my whole gain equation out first. So I can V out over Vs, right? That's going to be equal to the gain from node 2 to node 1. So I'll write that as V2, but node 1 is Vs, right? Times the gain from node 2, sorry, from node 1 to node 2, I should have said before. And then from node 2 to node 3, that's going to be V at 3 divided by V at 2. And then finally the gain from node 3 to node 4, where node 4 I've already recognized is my output voltage. So that's what my gain is going to be. And I'm going to get each of these gains one at a time. Right? So let's first get this first gain here, V2 over Vs. If you look at that, that's the gain across this resistor Rs. That's just the voltage divider. Right? So I only have two. I see this resistor. Looking into Q1, I see a resistor. There's no transistor gain here, so I don't have to worry about GMs. And so I only get a voltage divider here, and that voltage divider is just going to be whatever the resistor is seen looking that way. But remember, that resistor was Ri. Sorry, that way. That resistor was Ri there. So I can just write this as Ri over Rs plus Ri. Okay, and then I can plug in what I had for Ri here, which I'm going to go ahead and do just to be complete. So that's my RBB in parallel with this R pi 1 plus beta 1 plus 1 times RE1 divided by RS plus that same other resistor, RBB, parallel with R pi 1 plus beta plus 1 times RE1. Okay, and that's my first stage there, and that of course is just the gain across a voltage divider. And of course a voltage divider doesn't have gain, it's more like an attenuator, but I'll still call it a gain. It's a transfer function from node 1 to node 2. Okay, now the second thing, I have to get the gain from node 2 to node 3. And so now I want this gain, let me go across here. So I need V of 3 divided by V of 2. And this gain I can recognize as a transistor there. So I need to know the gain from the base of Q1 to the collector of Q1. And so here's where you need to know your inspection analysis equation. So if I bring this up here, we're looking for base to collector gain right here. And so that base, whoops, this one, base to collector gain. And so that base to collector gain is right here. It's equal to VC over, or VB is equal to minus capital GM times RC circle. But remember, C circle is all of the resistance from that node to ground, from the collector node to ground. That's what that means. Okay? And then GM is this, little gm divided by 1 plus little gm times RE. And I'm just going to use this formulation now to write out the gain from node 2 to node 3. So let's take this down again, go back to our circuit, node 2 to node 3. This again is going to be minus capital GM of stage 1, make that minus sign bigger, times all the resistance at the collector of Q1 down to ground. Okay? And so I'm going to write this in. So I know what that GM is, and we just looked at it. That's going to be that little GM1 divided by 1 plus GM1 times RE1. That's what big GM is equal to. And now I multiply this by all the resistance I see from the collector node to ground. And so what's that resistor going to be? Well, if I'm at this node, if I look up this way, I see RC1 to ground. Okay, so that's going to be one of my resistors there. So let me make that one big resistor. So I have RC1 to ground. And that's going to be in parallel, though, with the resistance I see looking down into Q1, which we already determined before was R01 times this big thing. And you know what I'm going to do. I'm going to neglect this later on, but right now I just want to be very complete to show you everything before I start neglecting things. So here's that resistance. Okay, looking down the collector of Q1. So I've got that resistance, I've got that. But remember, I need the resistance from this node to ground. That means I have to look this way too. I have to look in the Q2 direction as well. So I have another resistor in parallel with this. That will be this, and I'm going to write that there since I'm out of space. But that's going to be that resistor. Well, we haven't looked at that resistor before, right? So if I want that resistor looking in this direction here, what is that resistance looking in that direction? So I already wrote some of it there. There's R pi 2. Now maybe I'll just write it here and not there. But I've got R pi 2 looking into Q2. But then, remember, you just told me you got to multiply all the resistance you see looking out this way by beta plus 1. Right? And so the resistance looking out that way is going to be equal to beta 2 plus 1, since that's the second transistor, times RE2, parallel with RL, okay? And even in parallel with the R0 of 2. We're looking that way, right? Because that's also coming up from that node out to ground. Okay, so this now becomes the resistor that fits in that little circuit there, that little circle there. Okay, and so I've accounted for all of these resistors here, but you know what I'm going to do. I'm going to look at this and I'm going to say, okay, this thing is large. Okay, and I'm going to say this thing is also quite large, right? It's beta times some big resistor there. Okay, plus an R pi there. And so in the end, because those are large, I'm just going to say that my gain from V2 to V3, there's no one out there, okay, is just going to be equal to minus this first term, GM1, but times the resistance that I'm left with, which is just RC1 now, divided by 1 plus that GM1 times RE1. This is now the gain from 2 to 3. Okay? Any questions about what I just did there? Okay, so I'm going to finish the gain now, because all I need now is the gain from 3 to 4. And so let me do that in blue. So I'm going to write the gain from 3 to 4, that's V of 4 divided by V of 3. This is going to be equal to, and if you remember the inspection analysis equation, right? We're looking for that equation for, and you know what I'm going to do, but I'm going to do this slow, nice and slow for you, right? We want base to emitter gain. And so these are the various forms of base to emitter gain equations that we have here. It's whatever resistance you see hanging off of that emitter, making a voltage divider with the resistance little re, which is 1 over gm. Okay? And so if that's the equation we're going to use, then let's go back. Let's take a look at this. So I'm looking here. I got little re right there, essentially, and that's making a voltage divider with all of these resistors. So all of these resistors are RE2, parallel with RL, parallel with R02. Then I'm going to divide that by little RE2, plus that big RE2, parallel RL, parallel R02. Remember that little RE2 I can also write as 1 over GM2 if I wanted to. That's a pretty small resistor compared to this RL probably. And so this whole thing is going to be about equal to 1. And so in the end, now I've determined all the sub-gains that I need for my total gain. And so I can now use all of the little equations that I just derived there for each of the smaller sub-gains, and finally write my total gain from Vs to V0 is just going to be equal to, right, my V2 over Vs gain times my V3 over V2 gain times my V4, which is V out, over V3 gain, which is then going to be equal to, finally, oops, uh-oh, how come there was nothing here? Looks like I skipped a page there. So I got to look at all these gains. So there's the first gain, that RBB, parallel with R pi 1 plus beta 1 plus 1 times RE1 divided by RS plus that quantity. Okay, that was my first gain stage. The second gain stage is going to give me a negative, so I'm going to bring that negative out here. Okay, and that's going to be multiplied by the capital GM that I had, which we knew was this little gm, well, I'll just write that gain thing. Little gm1 times RC1 plus divided by 1 plus little gm1 times RE1. Okay, and that's it. That's my gain. Okay, so you see what I've done. I've very simply written down that gain just by looking at the thing. I did not draw a single hybrid pi model. I'm just looking into the terminals. And when I look in the terminals, I see my memorized equations. If you can do this, you're going to be very powerful with this, because the sky's the limit on how large a transistor circuit you could do this to. So at some point, you know, maybe we'll look at the 741 op amp that you're using in lab, and I'll show you its full circuit. And maybe I'll be able to show you that you can actually analyze that and determine the gain of the 741 by just analyzing that. 741 has something like 40 transistors in it. Okay? And so with that, you know, if we have the time, if I could actually do that, we will do that sometime in this class. We'll see if we have the time to do that. But for right now, let me grab this thing, which I'll append to that other side there. But this is just summarizing the procedure that we just did. Okay, first thing we do is get the DC bias point, but then we identify and label all the signal path nodes. We get the stage gain from node to node. For each stage, you notice as we did that, we were accounting for the loading by the next stage. Always look at the next stage, include its input resistance in with your resistance calculation. For transistor terminal to terminal gains, you'll need to determine the output node resistance to ground. And so you include loading by the next stage for this too, and even the influence of loading by the previous stage. You have to include for that. Take the product of all node to node gains to get the total gain. And you can do all of this by inspection if, one, there's no feedback. Okay, so in this circuit we just analyzed here, there was no feedback. Right here. Right? You don't have any feedback. If there's feedback happening, like from here to here, then you got to be careful. Okay, and if you look at my exam and you think you see feedback, think twice. Right? Because it may be feedback, it might not, depending on what kind of thing you're trying to find. You know all the terminal gain equations or can see and derive them quickly, then you can do inspection analysis. If you know all the equations for resistances, looking in the transistor terminals to ground, or can see and derive them quickly, then you can do by inspection. And see or derive quickly can often be done by following the currents, right? If you don't remember whether it's multiplying beta plus 1 or dividing beta plus 1 when you're looking at resistances, you can figure that out by just thinking of the currents. Okay, and derive that very quickly. Okay, so some very powerful techniques that you've seen today, and hopefully you can apply in the future homeworks, maybe even on the exam if you dare. Although in the exam, if you just want to do hybrid pi, that's perfectly fine. Do what's comfortable for you on the exam. Right? I'm trying to push you into doing this inspection analysis, but if you're not comfortable with it, don't do it. Okay, do what's comfortable with for you. Just understand that if you're not doing it, it'll take you a longer amount of time. You'll be working furiously, but probably 2 hours is enough to get the whole thing done. But what do I know, right? That almost is never true in the end. Okay, but that's it for today. I will see you on Wednesday next week.